So just a disclaimer on this section, I won't be offended if people who aren't that interested in building models want to go at this point. This is going to be mostly about some more advanced ideas in inference. The other disclaimer is I'm only going to touch on them very briefly, so hopefully this is fairly quick. This is mostly to serve as a highlight of what is out there if one wants to do efficient Bayesian inference in more complex models. So with that in mind, let's go. Once I get my mouse, there we go. So this has come up a few times in a few questions. One of the major alternatives to map estimation and MCMC methods is variational inference, right? So map, in some sense, is the computationally easy but poor quality approximation we can make. MCMC is the slow but good one, right? Or slow but good approximation. Right? And so these are somewhere on a continuum and at each end of the extreme. But there are other approaches that fall somewhere between these two. And you can make different trade-offs between computational complexity and accuracy. So variational inference is one of these approaches. In practice, variational inference is not that much more expensive than doing map estimation, but it has a huge benefit, which is that it actually estimates a distribution. Even if it's a bad distribution, it's better than, most of the time, better than the point estimate of map, right? In fact, map is a degenerate case of variational inference. The reason variational inference is interesting right now, it's been around, at least in the statistics, the Bayesian stats literature, for probably about 20 years at least, getting on that. But I think in the last 5 years, things have really picked up. And one of the key benefits is that it's now much easier to apply variational inference to a much broader class of problems. The basic idea of variational inference, instead of trying to sample to approximate the posterior, we come up with this optimization problem, where the goal is to take our approximating distribution, Q, and try to find one that is as close as possible, in some sense, to our posterior. So the typical way we measure closeness in VI, in variational inference, is through the KL divergence. There are other things you can do, but this is the most common one. And it turns out to be that you can rewrite it as the difference of the expectation under your approximating distribution of the joint, log of the joint, and then this other term, which is actually the entropy of your approximating distribution. And you can ignore the constant factor, the normalization constant, and focus on optimizing this, because this term doesn't depend on the variational parameters we optimize, right? So this is commonly called the elbow. The key thing here is that the expectation is computed over our approximating distribution, not the true posterior. So if we assume a fairly simple form for our approximating distribution, sometimes we can actually do this computation. In other cases, we can at least approximate it with Monte Carlo approaches. Now, if you were to pick up probably a standard reference on variational inference, the first thing you would see is mean field variational inference, right? And it's the most well-established approach, and you may also see it called variational Bayes sometimes. The key assumption is that our variational distribution can be rewritten as a product of distributions where we have one term for each parameter in the model. You can relax that. It doesn't need to be each parameter. It can be blocks. But the general idea is that we have multiple different distributions which model some part of our parameters. Now, the nice thing about the factorization, it has nothing to do with the model. This is just an assumption we're making on how we're going to approximate our posterior. And the nice thing about the mean field is it's typically easy to come up with an efficient inference scheme that looks a lot like EM, at least within certain classes of models within the conjugate exponential family. If you're outside that set of models, then this expectation you need to compute becomes hard. And we'll talk about some ways to do that in the next slide. So the main deficiency of mean field variational inference is just by design, your approximation can't capture correlation between variables. You're using two completely independent functions to capture the correlation. So suppose the level sets of your true posterior is something like this, right? I'm not going to be able to draw a perfect circle, but your VI estimate's going to be something like this. This is meant to be a circle, should be round. And it's round because there's no correlation. It's an uncorrelated Gaussian. That's what I'm trying to communicate. So this sort of key insight in recent years has been that one can use Monte Carlo methods to compute these hard expectations. Not MCMC, but Monte Carlo, straight Monte Carlo. And the key thing we need to actually be able to do to optimize the KL divergence is to compute the gradient with respect to the variational parameters. And here we see those expectations appearing. Now, there's a couple of strategies. One that's really popular in the deep learning world is to reparameterize the variational distribution so that the objective is differentiable. If you have heard of something called the variational autoencoder, which is wildly popular right now, that was the paper that introduced this trick. There's another idea, which is to move the gradient inside of the expectation and then use Monte Carlo to approximate that expectation. There's a bunch of work in this field. It seems like people favor the first approach right now. It's called the reparameterization trick. And I think this other one goes by the name of reinforce. Basically, the challenge for any of these approaches is that if the variance of this estimate becomes really high, then your stochastic gradient descent is not going to work, right? But the nice thing is, using Monte Carlo really removes a lot of the restrictions that we had about being able to compute expectations. Now all we need to be able to do is sample from Q. We don't necessarily need to be able to compute its expectation with our model, right? And so you can actually now start to design very generic variational inference algorithms. The key thing about variational inference in terms of how accurate it's going to be is how rich the family of models you use. So if you could use every possible model in the world, then you would actually recover the true posterior, because your KL, that's the only time your KL goes to 0. But if your posterior isn't within your family of approximating distributions, then you don't get there. The bigger your family, the better approximation you get. The other major highlight of variational inference work has been stochastic variational inference. In some ways, it's the same insight that we can use stochastic gradient descent instead of normal gradient descent to optimize the elbow. But the key thing here is that the gradient becomes stochastic because we subsample the data, right? So rather than having to evaluate the joint probability on every single data point, we can just pick 20, evaluate the gradient, take a step, do it again. If you do this on models like the latent Dirichlet allocation for topic modeling, you can, for example, apply it to all of Wikipedia now, whereas that would be sort of a wildly intractable idea for Bayesian inference previously. So this is all I'm going to say about VI for now. I just want to say it's exciting. There's some interesting literature. When should you use it? Well, basically, it's probably always better than MAP now. I can't really see any reason. Well, that's not true. But if you're thinking MAP estimation, you should maybe see if you can use variational inference in that case, because it probably will be comparable in computational cost. If you have massive problems, then it may be the most appealing thing to do as well because of the subsampling. So it's a straightforward exercise to rewrite the finite mixture version of the pi-clone model we had and implement variational inference for it, right? Then you could start to think about applying pi-clone to entire genomes in minutes instead of days, right? So it's an appealing thing. You will lose some accuracy, but it's not. It makes it feasible, which is interesting. All right. If you don't want to.
So can you say something about uncertainty estimates?
Uncertainty estimates. So with mean fields, you lose the correlation structure between variables that are in different factors. That's just the assumption of the approximation. In terms of the marginal variance of a single parameter, VI tends to underestimate it. This is just a feature of it.
How is the choice of distribution? So if you choose kind of normal distribution to approximate it,
Yeah.
does that also affect your error? I guess
Yeah, the worst, I mean, if your family of approximating distributions is wildly inappropriate, you'll get the closest one to your posterior, but what that means is...
So in a way, kind of the error shape is defined by the distributions you use to approximate.
Pardon me?
So the error is in a way defined, also determined by the distributions you use to...
Yeah, absolutely. This is what I was saying. This roughly saying when I say the bigger the set of distributions you can use, the better you do. So, I mean, one thing people are looking at is doing things like using neural nets as your approximating distributions, in some sense. Neural nets are really, really good density estimators. In fact, pretty much arbitrarily good if you have enough nodes. So if you can use them, you can do really well.
Converting that problem into optimization problem with a stochastic gradient descent, make like you choose a point, random point, and you try to evaluate the gradient. If the gradient doesn't exist, you can just try to do something like non-smooth analysis or.
So there's quite a lot of literature on applying better optimization strategies than just naive gradient descent. Things like that, trust regions, it's anything that's ever been done in optimization is now being done in variational inference, right? So once you frame the problem of inference as an optimization problem, then you just draw on that literature. That's the whole idea.
So one last question.
Yeah.
So when you do this version inference and you do like you probably do optimizations in the way iterative two steps in this gradient or whatever, do you think it's better to evaluate the algorithm to look at different like how so also when you have multiple initialization or something, is it better to look at the algo and see whatever it is, like the value of it, the loss basically? Or is it better to actually look at the fit in some way, measure that as a separate?
So the theory says so I skipped something here, which is this is an optimization problem. This is a non-convex optimization problem, so there are multiple modes. Gradient descent will not find the global, it will find the local optima. The heuristic to address this is to do multiple restarts of variational inference, and you'll get a bunch of different solutions, right? The way to pick among those solutions is to actually take the one with the highest elbow or the smallest KL. That is the theory. That is the one you take, not the one with the best joint. If you take the one with the best, the thing about the KL is it has an intrinsic penalty for over complexity in the approximating distribution. That's the entropy term. So if you just look at the joint, you miss that. There is, we just wrote a paper recently, very recently, on a really simple way that you can actually use multiple VI solutions within Monte Carlo, or within an MH move to basically use all of them to get the best of sort of. You know what, I'll take this one offline. There are some ideas on how to make use of all the solutions, but the theory says pick the one with the best elbow. And leave it there. All right, that was VI. That's an alternative to MCMC, but if you don't want to give up full posteriors, there are some better ways to do MCMC. So the core issue with Metropolis Hastings is that it can struggle on high dimensional problems. We talked about how you can block the variables and thus use Metropolis Hastings on lower dimensional subsets and thus hopefully solve the issue. Where blocking works poorly is if the posterior has high correlation between the two different blocks, essentially. In that case, you usually want to be able to update them both jointly, but the block strategy can't. The other issue with Metropolis Hastings is because it is a random walk, essentially, it can be slow to get between modes and posteriors. And if you start your train randomly near some local mode, even if it's a really bad one, you may get stuck there for a long time. So the first thing we'll talk about is simulated annealing, which addresses that problem of getting stuck way out in a local mode, given a bad initialization. And the basic idea is to introduce a sequence of distributions. This isn't the only one, this is a common choice though. P of beta, where all we're doing is we're raising our likelihood term to the power beta. We then have a sequence of values, beta 1 to beta t. In this case, we set beta 1 to 0 and beta t to 1. So notice that when this is 1, that's our posterior, right? Sorry, that's our joint distribution, I meant to say. And then if we're sampling from this thing, then we can sample from the posterior. Now, the point about this sequence is that it's usually really easy to sample from the prior. So if we start out at beta 1 equals 0, we're sampling from the prior, we can do that for a little bit. We can use any MC algorithm to do our updates. When we start at beta 1, we run that for some number of iterations. And then when we're done, then after, say, 1,000 iterations, what we do is we then change to beta 2 as our parameter. And we take the last value from the previous part, use that as our initialization for the next part, and run some MC algorithm. We keep doing that until we get to beta t. And then at that point, we start collecting actual samples, because hopefully we're sampling from the posterior. So hopefully we've done our burn-in by that point. And the intuition is typically your posterior may look like this, and you accidentally start out here, right? Then it's going to take you a while to actually get to where most of your density is with your random walk Metropolis Hastings. The point is the first distribution that you're sampling from, beta 1 equals 0, is some big flat thing that's sort of spread over the space. And then over time, you start to get slightly more bumpy distributions that get closer to your true thing as you go through this sequence of betas. And so if you go through this procedure, the chance that you move into this region increases, right? You want sequential distributions to be somewhat similar. If they're wildly different, then the chances that you end up in this high probability region are low, right? So that's the basic idea. In this context, that means that you want to choose your set of betas such that they're not too far apart, right? So you don't want to only use two values, one at 0 and one at 1, because then you're just jumping from the prior to the full joint, which is basically just random initialization, right? So you want to have a stepped sequence. Okay. Simulated annealing is like one of the oldest techniques. You can find it in almost any book. You'll often see it used for optimization. It's the same idea. If you're trying to do gradient search, you want to do it on the flat thing and then slowly heat it up, or cool it down, sorry. All right, moving to Hamiltonian Monte Carlo. This has probably been, I think this has become the most sort of popular sampling approach in recent years. And the nice thing about it is it's a really efficient way to update high dimensional continuous parameters. And it lets you do a joint update of all of them potentially, at least all your continuous parameters. And so the basic idea is that instead of doing a random walk, we use Hamiltonian dynamics to deterministically move to a new position. And the thing about those dynamics is they know something about our posterior distribution. They're not a random walk. They're not just taking a step left or right, checking. They're actually informed by the posterior, and specifically they know something about the gradient of that, or I should say the joint, not the posterior, right? So this idea is actually fairly old. I think it's been around since the 80s. It wasn't wildly popular because it's pretty hard to tune. There's certain parameters related to essentially how you approximate the Hamiltonian dynamics that this is very sensitive to. There's been some recent work provided, which has provided automated tuning strategies. So now you can sort of just plug in your density and its gradient, and this hopefully works well without much tuning. And that's been implemented in the probabilistic programming language STAN, which uses HMC, and it also uses another super interesting idea right now, which is automatic differentiation, to let people basically write models and then it automatically compiles all the sampling for you, right? So if you have a model that is all continuous parameters, it's worth taking a look at STAN because you may just be able to sidestep all of your actual MCMC implementation. And there are other probabilistic programming languages that are worth looking at too. The problem obviously is if you have discrete parameters, you don't have gradients and you can't do the Hamiltonian stuff. There's a couple solutions. One is to marginalize out the discrete part, which you can do in stuff like HMMs and mixtures. The other solution is just to block and use HMC on the continuous part and then do something else on the discrete part of the model, right? Pardon me?
Can you marginalize it out in the conditioning process?
No.
Probably not, that's an issue.
No, I don't think so. I would have to give that some honest thought, but as far as I know, no, you can't. Because you have, not unless you instantiate G.
So if you have a fixed number of K, you basically can use it.
If you have fixed K, yeah, if you, but not if you don't have K fixed, yeah. That's, if you look in the STAN manual, they have the example.
I've used STAN before, and it's hard to come up with a tune parameter for the leak Roth. They use the numerical integration for the, for the system of differential equation that they use for the, it is hard. I mean,
It is hard. Even the approximate solution they use isn't foolproof.
And also the coverage for the prior for the trees. I mean, if you work with phylogenetic trees, how to come up with like in yeast.
So somebody has done HMC for phylogenetic trees. The idea is essentially you don't try to make the discrete moves on topology. You basically, there's this trick if you shrink the branch length back and then extend it somewhere else. Anyways, there's this mapping you can do of phylogenetic trees onto a continuous thing and do HMC. How well it works, I don't know. In general, you don't want to, if you have discrete problems, Stan is not your go-to thing to do. There are other libraries, or you're going to end up having to implement your own thing. I mean, if you're doing phylogenetics, then rather than that, you look at Beast or Mr. Bayes, things that are tailored to that. But yeah, that's sort of the issue. So just a quick picture of what is HMC doing? Why is it better? So this is sort of the banana distribution where we have the posterior of 2 parameters that's this banana shape. So random walk, this is shown after 10 iterations, sort of just stumbles around out here in the tail because it's doing a random walk, essentially. HMC is able to make these very big jumps and get up towards where the mode of the posterior and start sampling from a high probability region pretty quickly. And then this is just some other version of HMC that has a clever weighting of some parameter. Pardon me?
That is Roth banana?
The distribution?
No. Oh, it's not having to do with this optimization.
No, this has nothing to do with cancer. This is just taken from a random HMC paper to illustrate the point. All right, so HMC is great for continuous parameters. The other thing that I'm quite interested in right now is sequential Monte Carlo methods. So SMC is a very general way to sample from high dimensional distributions. And the basic idea is you break your sampling steps down into a sequence of simpler ones. And you use a collection of what are called particles. So these are some representation of partial states. And so as you move through your SMC, in most setups, you tend to grow the representation. So if it's an HMM, for example, at time 1, your particles sample the initial state. Time 2, they then sample the next state conditioned on that, and so forth. At the end of the SMC run, then your approximation to the posterior is this weighted collection of particles. And so just by its nature, SMC has traditionally been used for models with sequential structure. It's where it sort of naturally maps onto. But actually, there's nothing that enforces that. You can use it on an arbitrary model. You just need to induce some sort of sequential structure. So there's some interesting applications. One of the ones has been in in phylogenetics. So one way to do that, to create a sequential structure, is to grow your trees upwards. So you start with all of your species in separate nodes, and then you connect 2, and then you connect something else, and your tree gets deeper and deeper. Let's see if I have a figure of this here. So here's sort of a schematic of how SMC would work. This is a slightly different setup than the phylogenetic one. This is a non-standard case where we're not increasing the complexity of our representation at each point. Here, what's going on in the background is they're actually running through an annealed set of distributions. That's the time points instead. But the basic idea of SMC is we have our particles, we have 3. We have these weights associated where the weights are roughly proportional to the likelihood. We propose a new move. So for example, this particle has swapped A and C. These ones have changed some branch lengths. And then at some point we do a bit of resampling to remove particles that are bad. That's the basic algorithm. So there's a really closely related idea called particle Gibbs sampling. And it's essentially taking SMC and using it in a blocked sampler. And the idea here is if you have a model like an HMM where you have this set of variables that are sequential or hard to sample any other way, you want to use SMC to do that, right? But then you also want to be able to update the other model parameters using Metropolis Hastings or anything else. So the particle Gibbs sampler does exactly this. It basically uses SMC to do one step and update a set of variables. If you do the completely obvious thing and just run SMC, draw a sample, etc., it's wrong. It doesn't work. There's this subtle thing you have to do, which is include one special particle, which gets you back to your current state, right? So you start, remember in MCMC, we always have a state at time t, and we want to update to a new state at time t plus 1. You have to have this special particle that gets you back to the state at time t. And that's conditional. That's conditional sequential Monte Carlo. So recently, one example of how this is useful, we recently developed a method for efficient sampling in Bayesian mixture models. So just to illustrate how this works. So up top, we have our data points spread around the space, and we have 4 clusters. What we're going to do is we're going to pick these 2 clusters. Actually, we're going to pick 2 data points at random and see what clusters they're in. And we're going to update all of these data points, or update the clustering of all of them simultaneously. This is what's called a split merge move in mixture models. And so at the end, after we've done our particle Gibbs, what we'll have is a new configuration where we've rearranged the clustering, right? The details aren't that important. Here we have the SMC. So essentially what we do is we decide where does the first data point go, which happens to be 3 here. We only have one choice. It just has to create a cluster. There's no other option. We move to the second time point. Now we're going to have data point 5. It has an option. Does it join a cluster with 3, or does it start its own cluster? We keep going with a bit of resampling and reweighting. And then at the end, we have our new clustering, which we sample from. The only thing that makes this different than the SMC we saw before is we have this one path here up top in square, which is the conditional path. And that is forced to get us back to here. So it's forced to make the sequence of decisions that gets us back to here. That's particle Gibbs.
Can you say something? Is this then, by using this, is this faster than SMC? Is it more?
So the problem is the basic Gibbs sampler that you use for Bayesian mixture models can get stuck in local modes very easily because it's only able to move one data point at a time. So to get to this configuration, actually this one's easy, this is a bad example, but if you have lots and lots, imagine you have 2 clusters, right? And the correct answer is to merge them together. Your sampler has to slowly move one at a time to the other cluster, right? And actually, the algorithm may be pretty well tuned, like the cluster parameter might be quite good for both of those. And unless you were to put them all together simultaneously, you would never actually see that that's a better solution. But doing the one at a time thing is never going to get you there. And that's, the Gibbs sampler fails because of that. Split merge move can say, you know what, all in one move, I'm going to put them together. Let's see what happens, and it will figure it out.
So eventually the convergence time gets kind of quick, is it? I mean,
What you say is the mixing of the Markov chain is better in some sense. It seems in some models that it's better to do this and you avoid the optima. I mean, the problem with Monte Carlo when you talk about these things is that if I run my Gibbs sampler forever, eventually it will get to the same place, right? But it may take, the sun may not be glowing when that happens, right?
for example, with the eye, in terms of speed.
Pardon me?
In terms of speed, it's somewhat slower, I guess, than BI, but it's quicker than MCMC. And it's kind of
Yeah, I mean, it's going to be on the order of MCMC. It's not going to be on the order of VI. It's just a slightly better MCMC. All of these can be thought of as slightly better MCMCs. They're going to be on that order, though, right? But what they will give you is some guarantees so that you're not just going to spend your time sampling around some small region of the space. That's uninteresting. Good. So parallel tempering is a very general approach to deal with the multimodal local optima thing. It's a little bit like sequential simulated annealing in the sense that we have this sequence of distributions. In fact, it's basically that sequence can be defined in exactly the same way. The difference now is instead of sampling with one distribution for a while and then starting with the next one and so forth, in parallel tempering, we run them all in parallel. We are running them all simultaneously. And then what we do is after some amount of time, we propose to swap the parameters between two of the chains, right? So the hope is we have this chain that I think of as the low one, which is sampling from the prior, moving around really well from the space. Sometimes it's going to propose a value that trickles up to the top, and when it does that, all of a sudden it's going to jump to a new mode, right? The actual details of how you move the chains around is kind of up to you. It can be any MCMC approach. So it's sort of a meta algorithm. The other nice thing is you can run the chains in parallel until you need to decide to swap. So there's some historical limitations to parallel tempering in terms of selecting the number of chains in the sequence of distributions. There's a recent paper from Alex Bouchard-Cote and Arnaud Doucet, which have this nice non-reversible version of this that seems to solve a lot of those issues. But sort of the schematic of what it's doing, if this is our state space, our posterior, and we have all these modes, is we have all these different chains. And what we're sort of showing here is the parameters. And then when we get these crossovers, there's a swap between a chain. And when we get a crossover, all of a sudden we're jumping over to this mode, right? So if you seem to have a hard to sample distribution with multiple posteriors, this is a potential solution. It's computationally expensive because you have to run all these chains, and typically it's on the order of, it's not the order of 4 or 5, it's the order of dozens, right? So you need sort of parallel computation to make it feasible, but if you have that, it's very appealing. The final thing is something that's this is going to be the last 2 slides. So the final thing we'll talk about is approximate Bayesian computation, and it's a very different flavor than anything else we've discussed. It's not about making MCMC more efficient. In fact, it's almost the opposite. It's probably the least efficient thing you can do. But it has a key feature, which is you don't need to be able to evaluate your likelihood to compute the posterior, which actually seems unbelievable given the way the posterior is defined in terms of Bayes' rule. Why is that helpful? Well, in a lot of fields, population genetics, for example, you have models where it's very easy to forward simulate data. Think of the Wright Fisher. It's very easy to generate data, write something to simulate a Wright Fisher. Quite hard to evaluate the likelihood, though. So if you can't evaluate the likelihood, ABC lets you just use the fact you can forward simulate data. Now, it's probably best just to jump to the picture here. The basic idea of ABC is we have some observed data and sort of a distribution on that. What we then do is we draw parameter values from our prior, and we put those into our simulator, our model simulator. So we run Wright Fisher and generate new data, simulated data. We then summarize that simulated data in some way, and we compare the values we get to our observed distribution. And if what we get is close enough to the observed data, we keep that sample and we add it to the posterior. If it's not, we just discard it. So these are all the open questions. First thing is, you don't just compare all your data typically. Like if you have high dimensional data, doesn't matter what your metric is, the bigger the dimension, the more your distance is going to get. So you need to compute some summary statistic like the mean, whatever. And so that's what you compare. And then you can use Euclidean, whatever else you think is appropriate. What does close mean? What is this value epsilon that says keep it or don't? That's also undetermined. You have to pick that. If you make it very small, you're going to reject most of your samples, and it's going to take a long time to collect samples. If you make it big, your samples will be not very close, and your posterior approximation will be quite bad. There's a lot of moving parts in ABC right now that people are trying to work out, and it's all these questions about how to pick summary statistics, distance metrics, this, that, and the other.
So you do summary statistics, you have multiple simulations, you do the summary statistic of this and that.
For each simulation, you compute a summary statistic. You say,
For a single one.
yeah, so you run 1 million simulations. For each one, you compute the mean. And for each of them, you then say, how does that mean compare to my observed data?
Mean over what? Mean over?
So values. Say it's a.
So you have cells, you could generate like a cell population, you could do the mean over how many.
Say it's the size of cells or something
Okay.
you're modeling, right? And then
Okay.
generate 1 million. You have 1 million that you observe, you generate 1 million, you compute the mean, compare. That's the idea. And it's incredibly, incredibly simple and shocking that it actually is valid. But it's an option. You should not use it if you can evaluate your likelihood. It's typically, maybe this will change, but it's less efficient than obviously using other methods if you can evaluate likelihoods.
It is hard to recommend for the sufficient statistic or a set of some of that describe the data is sufficient in the sense that describe the data. It is hard to.
No, there are no, so if you're outside the exponential family, there are no, I may be wrong on this, but as far as I know, you cannot have a sufficient statistic outside, other than the trivial one, which is all the data. That's why the whole, yeah. So you'll see examples of this done with Gaussians. In that case, it works really, really well because there are sufficient statistics for those who know what that means. Outside of really boring examples, it's harder. There's some theory on how to pick sufficient statistics coming out. I think Christian Robert and from Paris Dauphine, I think that is doing some work, and there's a bunch of other people in that sort of field. The theory is progressing, but this is fairly new. Like I think, 2010-ish is when this sort of was widely getting used, and it was a bunch of biologists who were, as far as I know, just winging it and doing this. Since then, it's proven to be a real thing. So, but yeah, basically, if you have really hard population genetics models, this might be something that can help you. Or we were talking today about sort of physical systems and things like that, where you can easily forward simulate. This might be one way you can put the data. All right, that is the end of this slide. So that was just sort of a highlight reel. Just to finish off with a few things, I have given you the GitHub link. The notes are there. The notes are incomplete right now. I will try to finish them. One thing particularly for this section I will try to fill in is the citations to sort of the useful references. If you see typos, things like that, let me know. I'm happy to fix them or have questions. And then otherwise, the only takeaway I'd say from this module is there is a lot of alternative approaches to map and Metropolis Hastings if you're going to be a Bayesian and probabilistic modeler. And the only thing I will say overall from this is hopefully you guys got the basic process of what we do. The sort of middle 3 modules really, we're trying to hammer that home. And I'll leave it at that.